Here, meet options. Okay. Awesome sauce. All right, hello everyone. Thank you for joining us today. My name is Kara Gordon. I'm the Partnership and Communications Coordinator for ECU's Center for Sustainable Energy and Environmental Engineering. I'd like to welcome everyone today to our webinar, excuse me, Energy Costs and Demands in Wastewater Treatment. Our mission at the center is to promote renewable energy technology and natural resource conservation through scholarly and applied research in effort to enhance industry awareness and best serve North Carolina communities. With research funding through the EPA's Pollution Prevention and Source Reduction Assistance Programs, center students, faculty, and affiliates provide valuable resources to businesses and industries across North Carolina. We offer energy, P2, and lean assessments and training largely to North Carolina automotive, chemical, fabrication, and food and beverage manufacturers. After conducting a facility assessment, the center additionally provides technical feedback and various business analyses. And we also facilitate certification workshops like Lean Six Sigma for sustainable and green manufacturing. And I'm excited to announce now that all of our webinar recordings are available on Facebook. You can like and follow us at ECUCSE3 to openly view all of the information that we've shared since June of 2021. I will also provide the link for easy access after today's recording. Before I introduce today's speaker, just a little bit of housekeeping. We're recording today's event, and as I mentioned, it will be available on our Facebook page. We encourage you to interact with our speaker today. We'll take questions at the end of the presentation, or you can drop them in the chat box at any time, and I will follow up at the conclusion. And then a PDF format of the presentation will also be included in the follow-up email. Additionally, I provide a link for providing feedback. If you could just take a moment, let us know how we can improve our future webinars. And then finally, we also provide a link to donate to the center, or you can simply go to give.ecu.edu/CSE3 at any time. We gratefully appreciate any contribution, large or small, as they help us to support student research activities, community engagement, and to continue to provide North Carolina industries with valuable information on becoming a better steward of environmental protection. So today we're honored to have Dr. David Ladner from Clemson University's Department of Environmental Engineering and Earth Sciences. Dr. Ladner joined the department in 2010 after completing a PhD in environmental engineering at the University of Illinois in Urbana-Champaign. I was born there, so I should know that. And a postdoc at Arizona State University. The Ladner Research Group studies physical and chemical processes for applications such as the removal of pesticides from drinking water, the removal of salt from seawater, and the treatment of high-strength industrial wastewater. They specialize in automated and remotely deployable membrane filtration systems and computational fluid dynamics modeling for process design. The ultimate goal is to increase sustainability and resiliency by lowering energy and life cycle cost in drinking water and wastewater infrastructure. Thank you, Dr. Ladner, for your time today and your expertise, and I will turn the platform over to you.
Okay. Thank you, Kara. It is fun to be here today. I'll get my screen sharing going. Let's see if this will work. And we'll start this up. So it is a pleasure to be here. I appreciate the invitation. We'll talk about energy costs and demands in wastewater treatment. And I have some co-authors here who contributed to this slide deck and the knowledge that went into this slide deck. So I appreciate Harish and Ashley and Mick for their help with this. Now, I want to start off. It's a Monday morning webinar, so I'll tell you a little carburetor joke real quick. A little boy, or a teenage boy rather, came into his dad's into the living room, and his dad was watching TV. He said, "Dad, there's a problem with the car." And his dad's like, "Oh no, there's a problem with the car." No father wants to hear that. He says, what's wrong with the car?" He says, "There's water in the carburetor." And the dad's like, "Water in the carburetor? What are you talking about? You just started driving. You don't know anything about cars. How do you know even what a carburetor is?" And he says, "No, I promise, Dad, there's water in the carburetor." And so that'll be somewhat relevant. We'll come back to carburetors in a minute. But these activities are part of the SCE3 program. So I think it's kind of funny. This webinar is CS, or it's hosted by CSE3, I believe. And our SCE3 is South Carolina Economy and Energy Environment. And I like that we're beginning this like cross connection or a collaboration in a sense here on this webinar. And hopefully it'll be the beginning of a lot more interactions that we can do from the North Carolina and South Carolina side. And our SCE3 program is really geared toward pollution prevention, energy and energy reduction. You know, the greenest watt is the one that doesn't have to be produced. And our goal, of course, is to save clients money by reducing their energy or power bills while maintaining the same or better productivity. And really, it's assisting folks with their particular needs, finding out what their processes are, and trying to help them with it. And we build on knowledge from the Department of Energy's Industrial Assessment Center. And I really appreciate the database that the Industrial Assessment Center has. So over the years, since 1981, you can see all the recommendations that have been, or the number of recommendations. In 1996, they peaked at over 6,000 total recommendations. And in blue are the ones that were implemented. In red are the ones that were not implemented, and orange is unknown. So you can see roughly about half the recommendations over time by the IAC have been implemented, and we're really building on that in our SCE3 activities as well. And the thing that has made the IACs an enduring source of information over the years is this database. So every recommendation that is made goes into this database, and it's built around this assessment recommendation code, or the ARC. And this is the front page of the PDF that is the assessment recommendation code. And if we were to go into that PDF and kind of see what it talks about in there, it's got things like number 2, energy management. Number 3, waste minimization, pollution prevention. Number 4, direct productivity enhancements. And if we dive into the subtopics, for example, with waste minimization, pollution prevention, they have 3.5, recycling, liquid waste, solid waste, etc. Let me see if I can do a laser pointer to make this a little bit more visible. The subcategories listed above, these are just a few examples, obviously, for this PowerPoint slideshow. There's many recommendations. And so when you drill down, they get somewhat specific. Like if you're changing your lights out for more efficient lighting, that has a specific code. The thing is, though, that wastewater treatment has received emphasis lately by the Department of Energy, but there's not as many specific codes for wastewater treatment, sort of just like general topic areas. So what we've been involved with our IAC at Clemson that we had the past 5 years or so, and with our SCE3 program now, is trying to really codify these recommendations for wastewater treatment. Now, this picture is a wastewater treatment plant in Columbia, South Carolina. And you might not be involved with a wastewater treatment facility. You might be involved more with manufacturing facilities or food processing facilities, other locations. Well, many of these facilities have wastewater treatment, and there are common elements. There are common unit processes that are used for wastewater in whatever kind of facility. So a lot of the things we're learning through through analyzing these wastewater treatment plants, essentially, or water resource recovery facilities, can be applied to a lot of other sectors when we're talking about wastewater. So why is energy a big deal at these wastewater treatment plants? Well, water and wastewater treatment accounts for about 3% of total energy use. And, we burn many barrels of oil, and we still burn lots of coal and more natural gas every year, and nuclear fuel. So 3% of the total energy use going toward wastewater treatment, that's a big deal. The total annual energy use by municipal wastewater treatment systems is about 30 billion kilowatt hours. And aeration alone is about 60% of the energy requirement for those wastewater treatment plants. So let's dive in a little bit to some of these unit processes that I was alluding to a minute ago. Incoming raw sewage will go through screens. This is not the way it's always done, but this is a typical process. You might have a grit chamber, a sedimentation tank, the aeration tank, and the sedimentation tank. One of the innovations of the past few centuries or many decades was learning how to do activated sludge by returning the sludge to the beginning of an aeration basin. That's really the secret to getting wastewater treatment to work well, because you're maintaining the bugs in the system. But those bugs, the bacteria that degrade waste and clean our waters, they need air. So this aeration tank, 0.3 kilowatt hours per meter cubed. So for every meter cubed of wastewater treated, we're using 0.3 kilowatt hours. And the total for the whole plant is 0.6 kilowatt hours per meter cubed to pump it around and to move it through all the other unit processes. You've got like chlorine peroxide or ozone over here for disinfection, for example. You might have an anaerobic digester. But the heart of the system is what we call secondary treatment, and it's taking 0.3 kilowatt hours per meter cube just to aerate the basin that's involved in that secondary treatment. So if you go to a wastewater treatment plant, or if you're looking at wastewater treatment in any kind of industrial facility, I want to pause here and ask you, what do you think are the most common energy saving recommendations? I alluded to air already, so probably some things are going to be related to the aeration system. But what have you done at your facility to save energy? And what have you done that could be applied to the wastewater side, perhaps? And then what would you like to do? So thinking about these things ahead of time is useful. And now as we dive into them, maybe you can predict a little bit of what I'm going to talk about in terms of specifics. From the IAC database, we can find some general trends. Now, what we did here is we queried the database, which I encourage all of you to do. If you're looking for ways to save energy, go to the IAC database and dig in and see what's available there. You can find it through IAC. Just search IAC database, and I think that should pull it up for you. Maybe include Department of Energy in your query to make sure you get to the right place. But you can search for different SIC and NAICS codes. So 4952 are sewerage systems, and NAICS 221320 are sewage treatment facilities. And when I ran this, there were 726 individual recommendations made through the IAC program at these types of facilities. Now, oddly enough, the first one has nothing to do with wastewater treatment itself. 120 of those recommendations were just utilizing higher efficiency lamps or ballasts. So even at wastewater treatment plants, the revolution in lighting is apparent, and you can save money by reducing lighting. But here's something more specific. Adjustable frequency drives or multiple speed motors on existing systems. Now, again, this doesn't apply only to wastewater treatment, but there are pumps and drives, mixers, etc., that can be run with variable frequency drives, and that can reduce the energy. Installing occupancy sensors relates back to the lighting. But then we have use or replace with energy efficient substitutes. So as good as the IAC database is, sometimes it's a little frustrating to find something like this that's very generic. It's basically just saying, do something differently or use some other process to reduce energy. So these 35 recommendations, we assume, have much more detail in them that we would like to drill down to. And that's this is the motivation for what I mentioned earlier, that we're trying to provide a finer level of detail about the types of recommendations that you can do. And some of these other ones are, again, more general, can be used for a lot of different facilities. But I will point out this: use a fossil fuel engine to co-generate electricity or motive power and utilize heat. This one is something that is specific to wastewater treatment, or at least when you look at wastewater treatment, you can analyze whether you can turn your wastewater treatment or your wastewater into methane and then use that to generate electricity. Some facilities are able to make that happen. Okay, so now 6 example recommendations is what we're going to do for the rest of this webinar here. One is demand management. This is one that does not apply only to wastewater treatment, but we have a ton of data available to us, and some of the key data is our demand data. So when we go to facilities and we ask them for 12 months of energy bills, we do an analysis. So here's the energy use in kilowatt hours. So kilowatt hours is the energy unit. And then here's the energy cost. So the part of the bill that is charged just on the kilowatt hours side. And you can see at this facility, it was, bumping up and down a little bit. And then the cost, August was actually a lower cost or a lower energy use. No, I'm sorry. This is just a place where there was kind of an aberration. We probably needed to dive into that data and see why they had a higher energy use in August, but sort of a typical or low cost. That's one way to look at it. And when you think about your power bill at home, that's the way you're probably going to think of it, because at home you're only charged by energy use. But electricity demand is often eye-opening to folks because the demand charge is kilowatts. So this is the power. This is the instantaneous draw on the system that you're using. Now, even though their demand charge was relatively constant over the 12-month cycle, you can see that they were charged much more during the summer months from May through August. And that's because the energy provider often does charge summer rates that are higher for demand. Summer is the time when everyone's running their air conditioners and there's a lot more load on the electricity grid, and so they're charging you more. If you're not paying attention to your demand charge, it can get out of hand. So what we've been doing is asking the energy company, the energy provider, for the 15-minute interval data. And so here is an example of the 15-minute interval data. This is the measured demand over time. And then here's the billing demand that was charged to this facility over time. And this particular facility was doing a good job of paying attention to their demand. I mentioned that summertime is when you have a higher charge for your demand, but also the demand rates can change. If you're a large industrial client and you're using a lot of energy and you're on a certain type of energy bill, then you're going to be charged on peak demand, and that's what's shown in tan here. So all these bars are the times of day when the facility is being charged extra for using power. And this would be in the afternoon, like 1 o'clock to 8 o'clock or so, I believe, at this particular facility. That can vary depending on your exact location and energy provider. So what this facility was doing, it was operating sort of a base load of around 900 kilowatts until that afternoon, summertime afternoon came, and they said, okay, let's ramp down our operations, and they were running closer to 550 kilowatts during the on-peak period. And then once that period was over, overnight, they would turn on their operations again and operate at their sort of base level. And you can see they did a good job. So the peak points, what we did for them when we analyzed their data is we added a dot to show all the demand times where that was during this peak demand period. And you can see all of the red dots are falling in this low 550. So a good example of paying attention to your demand and adjusting your operations if you can to operate mostly during your off-peak times. Notice this big white chunk right here, that's the weekend. If you can do a lot of your wastewater treatment or whatever operations you're doing during the weekend, then you can save on energy. Of course, your labor rate might be higher or something like that, so that's what you got to consider. So some example numbers. One facility, I believe it's a different facility than what I just showed here, but reducing demand by 382 kilowatt months at a rate of 518 per kilowatt month saved about $2,000 per year. So this was their billing demand, the blue circles, that was their actual demand. And notice this blue circle was kind of higher than average. So if this facility was able to meet a demand goal and keep all of their demand lower during that month, then they could save this $2,000 per year. Okay, example number 2, replacing surface aerators with fine bubble diffusers. This gets into the engineering of aeration. How do we get air into a system? Now, a lot of smaller wastewater treatment plants are going to use something like this surface aerator. The surface aerator is great because it's a relatively simple system. It's got a motor up top and a gearbox, and it's just spinning this mixer, and the mixer is located, right at the interface of the water and air, and so as it spins, it actually shoots air down into the tank. And it's convenient because it's relatively easy to maintain. The capital cost is relatively low for this mixer, but the standard aeration efficiency, or the SAE, for that mechanical mixer is 2.1 kilograms of oxygen per kilowatt hour. In other words, for every unit kilowatt hour of electricity that I spend, I can get 2.1 kilograms of oxygen into the water. But if you look at this fine bubble diffuser over here, the oxygen efficiency, or the aeration efficiency, is 5.75 kilograms of oxygen for every kilowatt hour. So in other words, you're using, or you're getting more than double, almost 3 times the amount of oxygen into the water per kilowatt hour than with the fine bubble diffusers than you are with the surface aerators. So this is really analogous to the carburetor that I mentioned earlier. Carburetors work great. They've been around for a lot of years. And you know what people say often for carburetors, or I don't know that people say this anymore, but when I was a kid, my dad would tell me about carburetors and cars, and he said that it was great that he could work on his car, he could work on his carburetor. And you could tweak your carburetor and fine tune it and whatnot. But over the years, we've come up with fuel injection technology. Now, fuel injection technology used to be only for like high-end vehicles. You know, it was expensive technology. You're not going to be able to work on your own fuel injector, you know, so the maintenance, you're going to have to ask someone else to do the maintenance for you maybe instead of doing it on your own. But, you know, fuel injection technology has come a long way so that it's not just for high-end vehicles anymore. Even just a quick internet search, I found this lawnmower, and it's a fuel-injected lawnmower that doesn't use a carburetor anymore, like most lawnmowers used to use carburetors. The same is true in the aeration space. Technology has come a long way. There's still some motivation and impetus for using surface aerators because of the capital cost and the ease of maintenance and whatnot. But the capital cost and the ease of maintenance for fine bubble diffusers has come a long way. We've learned a lot. There are many more vendors in the market that has brought the price down. So it's definitely worth considering switching over from this mechanical mixer to a fine bubble diffuser, because over time, a lot of energy is going to be able to be saved that way. Okay, example number 3. Thinking more about our aeration equipment, we want to automate our aeration using a DO probe. Now, there's a lot of facilities that have dissolved oxygen probes in their systems. It's kind of a standard thing in the SCADA system, supervisory control, and data acquisition system. You're probably going to measure your dissolved oxygen inside your aeration tank. And a typical goal is 2 milligrams per liter, which I think is kind of interesting. You know, for a healthy stream, especially if you have trout or fish in it or something like that, it's going to be more like 8 milligrams per liter is what you're going to want to have. But in a wastewater treatment system, all you really need is 2 milligrams per liter of oxygen. If you over aerate, you're actually not helping your process go any more efficiently than providing typically around your 2 milligram per liter. But wastewater flow rates come and go. You know, you've got like lower wastewater overnight, more wastewater in the morning. If you're running your aerator, this on the right is a big blower providing the oxygen to the system. And if those motors are running at the same speed all the time, then they're going to be providing more aeration than is required during those low flow times, or just because, you know, maybe there's less waste in the water at a particular time. So what you want to do is have a DO probe in there and actually connect your system to operate on the DO probe. You might be surprised how many times facilities have DO probes and they have the capability to automate it. They don't quite trust their DO probes. There is a lot of work to make sure your probe is working correctly and to make sure the automation is happening correctly. You know, the operators do need to be paying attention. But if they can do that and let the system control itself with a DO set point, then energy can be saved. Example number 4, installing VFDs for motors. Now, I alluded to this earlier because VFDs was one of the things that showed up in the database analysis as a typical recommendation at these facilities. Variable frequency drives is what these are. They can match the utility energy consumption to the system energy requirements. And it's really about changing the torque of the motors. And perhaps a lot of you have heard about VFDs before. I have this table, which I need to go back and edit some more, but let's dive into this. If you're operating a system for 2 hours, 3 hours, 5, up to 24 hours a day, and if what you really need on your system is 100% speed of that motor versus 90 versus 80, 70, 60, 50, if your motor is actually running at a constant speed, then you're going to be using like 40 horsepower hours here, 60, 100, 140, etc., and it's going to cost you this much. But if you have it on a VFD, you're going to be able to decrease that cost because you're only running at 90% of full speed, it's going to be 54 horsepower hours instead of 60 horsepower hours. Of course, if you're down at 50% speed, it's going to be 30 horsepower hours for this part of the time versus 60 horsepower hours. So overall, your cost per day using constant speed was $39 in this example, $39 per day, and using a variable frequency drive, $28 per day. Now, the deal with VFDs, of course, is capital cost, like so many recommendations. So you need to do an analysis and see if the capital cost of installing the VFD is going to make it worth the savings that you'll find over time. But this is the kind of analysis that you can do to evaluate your VFDs. Now, VFDs can be used for pumps or mixers, or even those blowers. Example 5 is one that's a little bit different, not as commonly discussed, but peracetic acid is kind of an up-and-coming chemical in that it's being used at more and more wastewater treatment facilities, and especially at smaller facilities, they're finding good avenues for peracetic acid. A lot of times peracetic acid, so this is the chemical formula for peracetic acid on the left, it's really good at killing bacteria. In fact, it's used as a disinfectant in a variety of different settings, but wastewater treatment has become one where it has been used more and more. So ultraviolet disinfection is also a relatively new technology that's been installed in the last few decades, but it does require quite an energy draw. So combining peracetic acid with the ultraviolet disinfection is a way to perhaps decrease the energy use. And at the same time, you're giving yourself two different avenues for killing bacteria and disinfecting your water. So it gives you a little bit of more fine-tuned control over the system. And of course, the peracetic acid is going to cost some money, but over time it could be less than the UV disinfection. Now, some of the analysis we've done lately for the cost of peracetic acid, it's not beneficial. But over time, the costs are going down, so it's something to pay attention to as things progress. And then example 6 is kind of another different sort of thing that I wanted to bring up. This one highlights the benefit of having a third party come in and look at your system, because sometimes you're doing things that you've sort of forgotten that you're doing, and then someone else can come in and say, well, why are you doing that? And help you think through how to make improvements. So at this particular industrial wastewater treatment plant, it's a really cool plant. To be honest, though, it's quite over-designed. Like they're really hitting their wastewater hard, and they have a lot of tank capacity for the low flow rate that they have coming in. But the funny thing is, they had these two settling tanks, and I believe they were using them as digesters, aerobic digesters. But when the students came in and we did a drone flyover of the facility, we noticed that this plant had something in it, and it was growing weeds and trees. It didn't look like it was in operation. And they said, oh yeah, we had some off-spec material that we had to just throw somewhere, so we put it in that tank, and we haven't used that tank since. Well, that tank capacity is a useful thing. You know, they're able to operate with this particular tank, but having the secondary tank online would give them a lot more operational flexibility, and we realized that it could reduce their truckload frequency if they had this tank and filled up their material, so they could do larger truckloads, fewer trucks. And so this was going to be an energy savings and a cost savings for that particular facility. And we totally recommend having an outside person come in, like ECU has their assessments that we do. Here at Clemson University, we have folks that we send out too. Take a look and see if there's anything like this that you can improve. So a few other observations or considerations that we've kind of gathered over the years of doing these assessments. A key thing is energy savings measures need to be balanced with treatment effectiveness considerations. And we get that. And anytime we offer a recommendation, this is usually the first thing that people mention is that, well, yeah, we could reduce energy, we could reduce our dissolved oxygen level or something, but we want to make sure that we treat the water, and we get that. And certainly your first goal for any wastewater treatment system is to make sure the water meets your permit levels and even exceeds your permit levels going out of the plant. So that is part of the assessment that we do. The field would benefit from evaluating energy savings from past upgrades. So oftentimes we have SCADA data, the supervisory control and data acquisition data, but we don't often use them. So when we make changes to our process, is someone really going in and evaluating, the before and after, and seeing, how did the plant set points change? Getting in touch with the utility, the electricity provider, and seeing if your demand numbers really had a shift when you made that process change. That's another thing that we're interested in helping people do, is analyze that data. We're considering also inviting retired engineers and operators to volunteer their time. And there's been a few people that have been willing to do that. They know a lot about how to operate these kinds of facilities, and they're interested in helping out and kind of giving back to the community. So that's something we're looking into. And then often plants need to hear the same recommendation from several sources to act on an idea. So maybe you're hearing about something for the first time in this webinar, or maybe you have a client that you're going to go work with. You're probably going to need to mention it to them once, and they might need to talk with a consulting firm or a vendor, and then they'll hear it a second time to really decide that they want to make that improvement. So it's worth keeping up the conversations. So again, I want to thank, in particular, Larry Kemp at Renewable Water. He was instrumental in giving us access to the facilities and letting us come in and make some recommendations for their facilities. REWA is Renewable Water, and that's the wastewater utility in Greenville, South Carolina. I think they have 7 different treatment plants, and we did analyses on 3 of their treatment plants over the years. And Harish Srinivasan was a really good graduate student who put together a lot of the recommendations that we made at facilities. Ashley Martin also worked with Harish on that. And Dr. Friedman has been at Clemson a long time, and he teaches our wastewater class, and he has done a lot of this analysis and helped us come up with ideas as well. Now, I do have a few additional slides that I could dive into, but I wanted to keep it to about this time frame to see if we could foster some discussion, see if anyone has things they want to bring up. So I'll go ahead and stop sharing my screen if I can figure that out right now. Okay. And open it up if anyone has questions or other ideas for energy savings recommendations that they'd like to bring up.
Dr. Salam dropped a couple questions in the chat box. I didn't know if he wanted to unmute and ask those himself or... Okay, so I'll go ahead and ask them. Oh, there he is. Okay, you're muted.
Okay, you can go ahead if you want. That's fine.
Yeah, go right ahead.
Well, I can. Oh yeah. Do you want to state your question, or should I just read it?
Okay, I will do it quickly. So I was simply asking, out of these recommendations, some already are accepted by the facilities or facilities in general, and some are not. So what is the least and what is the most implemented or accepted recommendation out of these ideas? So which one they accept easy, which one they resist to? And also, do you do any measurements after implementation, like if they inform you that they implemented one of these recommendations? Actually, I noticed that after I sent the question, you said you follow up with the demand management. So I guess the answer is yes. It's a long question.
Yeah, I'll answer that last part first. The answer is yes on the follow-up, but I always wish we had more time to follow up and really analyze data after the fact. So much just depends on the client making the request, and then we'll go ahead and do that. And as far as measurements that we've done some compressed air tracking. I didn't talk so much about compressed air. The blowers, we don't consider that compressed air. But on the compressed air side, evaluating compressors, we have gone in and put sensors on there to kind of see how often the compressor is operating. And that's often useful for the facilities. But as far as the most often implemented recommendations, the demand management is actually one of the easy ones to implement. So I think easy to implement and often implemented go together, right? But when you realize that you can start analyzing your 15-minute interval data, and you realize that the power company has those data and they're willing to provide them to you, or maybe you already have access and you didn't know it, then getting on a routine to analyze that data and make sure that when your peak demands are is kind of an obvious thing to do. And then the ones that are hardest to implement are the ones that have the biggest capital cost. Like, for example, if you're going to install a combined heat and power system to try to utilize methane from anaerobic digesters, I don't know of any facility that actually did that multi-million-dollar upgrade just based on our recommendation. So those are two quick ones that I can think of.
Okay, thank you.
Mm-hmm.
I have a question. I was hoping that you could retell the punchline to your carburetor joke because the internet cut out just as you were giving the punchline and we didn't get it. And hopefully, if you tell it again, we'll get it all in full perspective.
Okay. Yeah, he said it was a short punchline. So the kid tells his dad, "There's water in the carburetor," and his dad says, "Oh no, where? Okay, let me look at the car. Where's the car?" And the boy says, "It's in the pool."
You were just coming back as you were finishing up that punchline, so I wanted to make sure that everybody got the punchline to that joke so that we could understand the full perspective of that.
Perfect. Yeah, this is one of the disadvantages of of Zoom is you can't read the audience to know whether they're laughing or not. So.
All right, so I know there are a couple other wastewater treatment specialists in the audience. Hopefully somebody would like to ask another question, or anyone from industry have any questions for Dr. Ladner today?
I do see one here from Miguel Rodas asking if a treatment plant detects significant amount of ammonia in the raw waste, what improvements would you recommend? Well, ammonia is going to be removed with extended aeration is typically the way we would go about it. So nitrogen removal in general is often going to require, longer aeration, and you've got heterotrophs are the typical bacteria. They're going to remove most of your carbonaceous oxygen demand. And that's what's going to be removed first and easiest. But then your ammonia degrading bacteria are going to need a little more tender loving care. So it's essentially just increasing the time of aeration. So it's going to take more energy to remove that ammonia, but it can be done, and ammonia is often handled in conventional wastewater treatment plants.
Fantastic. Thank you, Miguel, for joining us. Another question from him.
Mm-hmm. Yeah, to meet effluent limitations, many electroplaters rely on the use of waste segregation, thus relying on the use of pumps. Can you expand on energy efficient pumps? Yeah, so energy efficient pumps. To be honest, I think the way to go here is really talking with multiple vendors. There's so many pump vendors out there, and they all have their specific designs for the waste flow that you're interested in pumping. I was talking with a vendor at a conference actually, and they were showing me just the details of the turbines. So like for a centrifugal pump, for example, You can have two types of centrifugal pump. You can have the vertical turbine pump where the pump head sits down in the tank and forces the water upward, and that's got a very specific design of the rotor. It's like a fan blade essentially that pushes the water up, versus a typical centrifugal pump would have water entering the side. So anyway, the pump vendors, they're eager to sell you a pump, and it doesn't hurt to talk to multiple vendors and really find out what details they can give you on energy efficient pumps. So much depends on the design of that specific pump. And then, of course, variable frequency drives is another thing to think about. If your pump can be run at reduced capacity, or if it has variable flow rate, then putting a variable frequency drive would be good for pumps. Most of the time, though, I will say you can do pumping in batches so that you can just let the tank fill and then pump it all at once out of the tank, operate the pump at its most efficient point and most efficient frequency during that whole pumping period, and then just turn it off when the tank is empty. So sometimes tank capacity is actually the way to achieve efficient pumping, if that makes sense. All right.
Thank you, Miguel, for your questions. Anyone else with any questions? We can continue the conversation. All right. Sometimes it takes people a minute to type it out if they're typing it out, so I like to give them time.
For sure.
Okay, I can ask another question. Now, you mentioned just energy, right? But your work really is unique because you do pollution prevention and energy as well. So reducing the energy, the water consumption from the source, right, and chemicals will really have an impact on the wastewater treatment and also on the amount of energy consumed. Is this something like you recommended before implementing pollution prevention, before even look at the other options?
Yes, absolutely. So thinking about reducing our processed water needs is an example. And I'm trying to think of one facility that we looked at. You know, one interesting thing is rainwater harvesting. The biggest expense, this is on the same theme as I just mentioned, the biggest expense with rainwater harvesting is often just the tank to hold enough rainwater to make it worth your while. And then using rainwater, you usually need to treat it. We think of rain as being pretty clean, but you know, if it's falling on a roof and it's being stored in a tank, you're usually going to need to treat your rainwater as well. But especially, you know, as the years go by and water costs become higher and higher, looking at rainwater harvesting, especially for these big facilities that have a large rooftop area, is kind of an interesting thing. And I'd be happy to share kind of our previous recommendations, some numbers that we've calculated with rainwater harvesting as one example. And then we have another project, I'm trying to remember it, it's coming to mind, where we were talking about water recycling. Oh yeah. So this is actually in the hydroponics industry, so growing food with a hydroponic system. It turns out that a common way to grow food in hydroponics is to, you essentially do it in batches. So this particular lettuce facility, they were growing lettuce, and it's like 28 days of production. So they fill up their tanks with enough water water and fertilizer, and they just recycle that, or they recirculate that through the hydroponic system during the growth period. Some of the water evaporates, and of course the plants uptake the water and whatnot, so they have to refill, add new tap water to the tank. But at the end of the system, they have this water that's kind of dirty now because it's been operated for 28 days. It's probably got some bacteria and things in it. But the sad thing about it is they typically just flush all that down the drain, and it's got all the fertilizer in it. So they're supplementing with fertilizer to keep the fertilizer concentration at the same level throughout the 28-day cycle. So recycling that would be great to save the water, but saving the fertilizer might even be more interesting and more useful for the facility. So that's something to think about. It's a little bit of a challenge to treat that water, but it can be done, and I think the return on investment can be just a couple of years when you consider the amount of fertilizer and the water that's being lost. So those are two examples.
Looks like a comment from Sarah.
Yeah, she's saying, I do a lot of work with industrial dischargers. These can drive up required energy costs significantly when it comes to aeration requirements, suggesting municipalities to make sure to push reduction of waste to sewer upstream as well to lower energy costs. Yeah, that is a good. We definitely need to think about our whole wastewater ecosystem. There is an ecosystem. There's a whole collection system, right? And different people are putting different things into the wastewater. Thinking of it as a community and an ecosystem is a good way to go. All right. And then Sarah, someone else mentioned been both publicly owned treatment works and industry. Recommend the utility work with the industry to identify the costs and lowest cost places to treat. Absolutely. And Miguel mentions PFAS, removing PFAS from wastewater treatment plants. That definitely a hot topic that Miguel brings up, and I gave a seminar all about PFAS a few months ago. We were focused on membrane processes like reverse osmosis, and we were thinking a little more about drinking water treatment. If you have PFAS in your drinking water and you need to remove it, and you're using something like reverse osmosis, you're going to have that PFAS in your residuals. And in wastewater treatment plants, this is usually the place where the PFAS is going to be found, is in the solids that are coming from the wastewater treatment system. And this is a big challenge. Like, there are a lot of people working on different techniques to remove PFAS, but it's such a recalcitrant compound, and it's not biodegradable. And if you're going to degrade it with any kind of I'm trying to think of the different methods, like incineration. Even incineration, if you're incinerating your biosolids, which is really expensive, it might not get all the PFAS. So I guess what I would recommend is trying to identify the source of the PFAS and see if you can treat it upstream. So adsorption, activated carbon adsorption is effective for PFAS, and it's one of the cheapest methods that we have. Unfortunately, you're not going to want to do activated carbon adsorption on a whole wastewater stream, because there's so much other material that will just clog up or adsorb to your activated carbon. So if you can find the source of the PFAS and use activated carbon closer to the source, then that might be a viable approach. That's just my first couple comments, not knowing the exact system you're dealing with. Okay. And then another one, we did add aeration in the collection system to reduce aeration demands at the plant, determined it was low-cost option, best for the biology of the whole system. That's cool. PFAS destroyed in a gasifier on the biosolids. All right, that's great too. Biosolids with PFAS gasified, destroyed the PFAS. Yeah, if you have a gasifier, that's amazing. And if it's working for PFAS, that's also excellent. Okay.
Fantastic discussion.
Yeah, these are great. Thank you. Thank you all for commenting and asking questions.
Absolutely. Love the comments, love the questions. We have about 7 more minutes left in the hour. If anybody else has any more questions or comments that they'd like to drop in the box or ask Dr. Ladner, we're still here. Let's see here. Yep. And Okay. Well, if not, his contact information will be provided. I think it was on his presentation, but I can't remember if I saw it or not. If not, we'll make sure that it's on his presentation, or that we'll provide it to you in the follow-up email. If you have any further questions or comments or anything you'd like to ask him after the conclusion. And I'm not seeing any more. Sorry about that. Okay. All right, just getting some thank yous.
Yeah.
All right.
Well, I just want to say thank you, Kara, for organizing all this and sending out all the invites and reminders, and it's been fun. Appreciate it.
Yeah, absolutely. Thank you so much for your time today. Everyone's time today. We certainly appreciate it. Again, this recording will be uploaded by the end of the day on our Facebook page. I will make sure the link is provided in our follow-up email to make sure that you can access it easily. And just to let everyone know that our next webinar is in 3 weeks on April 25th, again from 11 to noon Eastern Standard Time, on energy saving opportunities, emphasizing compressed air and refrigerated spaces in industrial facilities. So we hope everyone can join us for that conversation and share it with your friends. We are expanding widely across the country, and we're happy to do so. Any questions, please feel free to contact us at sustainabilitycenter.ecu or at ecu.edu. ecu.edu. I'll get it right. Otherwise, we hope you all have a fantastic day, and let us know if we can do anything for you. Thank you so much.